All right, AP Chemistry notes, page 27. Most of this is going to be review from first year with a little bit more spice added in, looking at phase diagrams. Typically, you'll see it done like this, in which you have pressure on the Y, temperature on the X. And what it mainly shows is under what conditions do you have solid, liquid, and gas. And the major lines, zoom in on this, will show you the different phases. By major lines, I'm talking about this line and this line. I have the different names highlighted here. So we have, let's go with the normal ones first. If you go from solid to liquid, melting point, backwards, freezing point, liquid to gas, boiling point, backwards, condensation point. These two are a little weird. When you go directly from solid to gas, it's of course called sublimation point. And backwards is called deposition. Just think the gas particles are being deposited. That might help you there. A couple of special areas. This right here, where all three meet, is called the triple point. There's not a whole lot to say other than the fact that it's just a unique spot. Here's the critical point, sometimes called the critical temperature. That is the temperature at which, once you reach that temperature, it really doesn't matter what the pressure is. The particles are moving around so fast, they're going to behave like a solid, even if you have them fairly compressed. What's more interesting is to look at where water is unique. So this line here normally has a positive slope. And that makes sense because most things, if you take them in their liquid state, let's say that we're right here, and you raise the pressure, you will encourage them to become solid. If we go this direction, water is different. If you take water, let's say solid right here, and you increase the pressure on it, you go like this, and you actually can turn it into liquid. So if you were to take an ice cube and stick it in a vise and keep it at freezer temperature, so let's say your freezer is at -5 degrees Celsius, keep the ice at -5. If you were to compress it with the vise, you could turn it into liquid water even at that cold temperature because of this. The result of this is it causes water to have this odd line which slopes the other way, just in the boundary between the solid and liquid phases. That's special for water. There's one other substance that I can't think of right now that does it, but pretty rare. The reason why it does this is because when water freezes, it expands a little. So if you take a look at my drawing right here, this is a drawing of what water looks like when it freezes, in which case I have 6 water molecules. Each water molecule I've represented with a circle and then 2 dots. So the 2 dots are the hydrogen, the big circle is the oxygen. And so I have 6 of them all lined up. And they make this sort of hexagonal shape. And to do this, they have to spread out a little bit. That's what causes water to be this unique situation where the solid is less dense. Of course, that's why ice floats, icebergs float, and so on. It also causes an interesting thing in geology. Say you have a rock with a crack in it. So this is the rock. What happens is liquid water rains down in here, fills the crack. like so. Then the weather gets cold, and when the weather gets cold, the water freezes, and it actually expands and pushes on the rock and starts to break the rock apart. It's called frost wedging. It's one of the forms of geologic erosion that occurs. I have a better picture of water from an old overhead that I have, which I'll go to here. And this helps to see, there's a lot of water molecules, so it's a little bit overwhelming, but it helps to see the expansion that happens and these little hexagons that form. Now, these hexagons aren't absolutely perfect, but it's what the water molecules are trying to do. In between any two water molecules is hydrogen bonding, which has been shown in this diagram with these little blue dots. You have hydrogen bonding here, 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 so on, and that's part of how this all works. Holds the different molecules together. All right, is there anything else? Sometimes I'll do these problems in class right here. They're not super important right here, not a big deal. If we have time in class, we'll go over those. But otherwise, it's not a real critical thing. There's actually other things I usually like to do first. And that takes care of the note.